Sandhan, All Gujarat Integrated Classroom.
સેટેલાઇટના માધ્યમથી જોડતી કડી એટલે સંધાન.
Good afternoon. Myself is Professor Bhavin M. Patel, Assistant Professor in Mathematics, Government Science College, Gandhinagar. Today we will see the topic complex number from complex analysis. So function to this number, then mod z is defined like this: under root of x square plus y square, and this is denoted by symbol r. This will represent distance from origin to point xy in xy plane. હવે કોમ્પ્લેક્સ નંબરને રિપ્રેઝેન્ટ કરવાની જુદી જુદી રીત છે. એમાં આ એક છે, આ કાર્ટેઝિયન ફોર્મ છે. આ જે છે, this is a polar form to represent a complex number system where r is a modulus and it is obtained by this formula, and r is radius and theta is modulus, theta is argument of this complex number z, where r is given by this r square equal to under root x square plus y square, and x equal to r cos theta, y equal to r sin theta, and therefore theta equal to tan inverse y upon x. Now if we restrict this value of theta, if theta belongs to minus pi to closed interval pi, open minus pi to closed pi, then this theta is said to be a principal argument. These all things we know. Now see in the PPT, suppose we want to obtain principal argument of these two complex number. First one is this minus 2 upon 1 plus I root 3. Suppose we want to obtain the principal argument and modulus of this complex number. So first we will convert this complex number in its standard form like x plus iy. So multiply by its conjugate number, minus 2 upon 1 plus I root 3, multiply by 1 minus I root 3 and divide by 1 minus I root 3 through this complex number. So we will get is this minus 2 plus 2 root 3 times I upon 1 minus I square into 3. So denote I square equal to minus 1. So this is nothing but minus 2 plus 2 root 3 I divided by 1 plus 3, that is 4. So this is exactly equal to, because I square equal to minus 1. So this is minus 1 half plus root 3 by 2 times I. So we have converted this complex number in its standard form, x plus iy form. So we have x equal to minus 1 upon 2 y equal to root 3 upon 2. So the modulus of this complex number is r equal to under root of 1 by 4 x square plus y square and 3 by 4, that is 1. And suppose we want to obtain the principal argument of this complex number. Since x is negative and y is positive, so this complex number lies in quadrant 2. This complex number lies in second quadrant. So the principal argument is denoted by capital ARG is equal to pi minus modulus of tan inverse y by x. So we must have to evaluate tan inverse y by x, and we will substitute that value here. So now tan inverse y by x modulus of this is equal to tan inverse root 3 by 2 and 2. So 2 2 will be cancel out. So this is exactly equal to Now this is the thing, 2 1 root 3 30 60. So this is pi by 3. Tan inverse root 3 is pi upon 3. Therefore principal argument equal to pi minus pi upon 3, that is 2 pi by. This is the principal argument of this complex number z, and this is the radius of complex number r equal to 1, and principal argument is 2 pi upon 3. So see, in this is another example, second one. Suppose similarly we can obtain the principal argument of root 3 minus I raised to 6. So first we must have to convert this complex number in the form x plus iy. So here what we do is this, we will multiply this complex number by 1 upon 2 raised to 6. So root 3, see in the tally top, suppose if we consider this complex number z equal to root 3 minus 1 raised to 6, 1 or I, root 3 minus I raised to 6. Suppose we want to obtain the modulus of this complex number as well as its principal argument. So the technique is this, multiply by 2 raised to 6. So this will nothing but root 3 by 2 minus I upon 2 raised to 6. So first we will evaluate what is the value of root 3 by 2 minus I by 2 raised to 6. So root 3 by 2, now consider this complex number. So let me take this is 2 raised to 6 into z1 raised to 6, where z1 is equal to root 3 by 2 minus I by 2. So x is equal to root 3 by 2 and y equal to minus 1 by 2. So this complex number lies in the fourth quadrant. X is positive, x1 plus iy1. So x1 equal to root 3 by 2, which is greater than 0, and y1 equal to minus 1 by 2, which is less than 0. Therefore z1 lies in fourth quadrant. ચોથા ચરણમાં આવશે. હવે so theta principal argument, now tan inverse y by x. First evaluate this one. So tan inverse y by x is nothing but y1 upon x1 is equal to modulus of tan inverse y1 is minus 1 by 2 and this is root 3. So this is nothing but minus 1 upon root 3. So tan inverse modulus of tan inverse 1 by root 3, this is nothing but pi upon 6. Therefore principal argument for this complex number z1 is equal to, this is exactly equal to minus mod of tan inverse y1 upon x1, so minus pi upon 6. Therefore we can write down this, our main complex number z1 is equal to 2 raised to 6 into cos minus pi by 6 plus I sin minus pi upon 6 raised to 6. Now we will apply the Mobius theorem to this. So we can enter this 6 to here. So cos minus pi plus I sin minus pi. 6 will be cancelled out. This is the De Moivre's theorem, because this is the reason. Cos theta plus I sin theta raised to n equal to cos n theta plus I sin n theta, because of this. So this is nothing but 2 raised to 6. Now cos minus pi is minus 1 and cos pi is minus 1 and sin minus pi is 0. So this is exactly equal to minus 2 raised to 6. So our main complex number z is equal to minus 2 raised to 6. Therefore, principal modulus of this z, mod z, is nothing but 2 raised to 6, and principal argument is equal to, this lies in on negative x-axis, so this is nothing but pi. So this is the thing. So now see in PPT, there are more examples of modulus and argument. Z equal to 1 plus 2i divided by 1 minus I raised to 2, and second one is this 1 plus I root 3 raised to 12 upon root 3 minus I. In the second example, we will multiply and divide by 2 raised to 12. There are more examples. Find the modulus and argument of the following complex number. So let me take third one. It is little bit different. Z equal to 1 plus I e raised to I pi by 6. Suppose we want to find the modulus and argument of this complex number, and first we will simplify e raised to pi by 6. This is a exponential form of complex numbers, so this is nothing but cos pi by 6 plus I sin pi by 6. Cos pi by 6 is nothing but root 3 by 2. I sin pi by 6 is nothing but 1 upon 2. So the whole complex number is this, 1 into root 3 by 2 is equal to root 3 by 2 minus this plus I root 3 by 2 plus 1 by 2. So this is nothing but root 3 minus 1 upon 2 plus I into root 3 plus 1 upon 2. So both are positive, x and y. Therefore this complex number lies in the first quadrant, and the r is equal to r square equal to root 3 minus 1 whole square divided by 4 plus root 3 plus 1 whole square upon 4. By simplifying this one, we can obtain r, and similarly, as we have seen, we can obtain also principal argument. So see the next example. Find the real and imaginary part of minus 1 minus I raised to 7 plus minus 1 plus I raised to 7. અહીંયા તમારે 2 raised to 7 થી મલ્ટીપ્લાય અને ડિવાઇડ કરવા પડશે. Let me take this one. Suppose we want to obtain real and imaginary part of this complex number z minus 1 minus I raised to 7, minus 1 minus I raised to 7, yes, and minus 1 plus I raised to 7. So multiply and divided by 2 raised to 7. So this is nothing but minus 1 by 2 minus I by 2 raised to 7, and this is nothing but minus 1 by 2 root 2, root 2 raised to 7 plus I upon root 2 raised to 7. Now this is minus 1 upon root 2. The complex number lies in third quadrant, so this can be written like this: root 2 raised to 7 minus 1 by root 2 minus 1 upon root 2. That is, angle is pi by 4, minus pi plus pi by 4. So minus 3 pi by 4. So this is cos minus 3 pi upon 4 plus I sin pi by 4 raised to 7 plus similarly here this complex number lies in x is positive and y is negative. X is negative and y is positive, so this lies in the second quadrant. So this is cos 3 pi by pi minus pi by 4 plus I sin 3 pi by 4 whole raised to 7. Now by the Mobius theorem we can enter this 7 inside this n cos function. So this will be minus cos minus 3 pi is minus 21 pi upon 4. Similarly here, so this is nothing but cos. Now cos is even function, 21 pi by 4. Sine is odd, so we can take this minus plus, okay, and plus cos 21 pi upon 4 plus I sin 21 pi by 4. So this will be cancelled out. So this is nothing but root 2 raised to 7 into 2 cos 21 pi upon 4. So this is exactly equal to 2 into root 2 raised to 7. This can be written like this, cos into 5 pi